Hello, I am DJ, and joining me here today is Logan and Brian, and we will be presenting to you about visibility in our national parks. Visibility is of great significance to the National Park Service because much of the allure of the parks is the visual scenery which can be found in them. When the visibility is reduced to the point that things like mountains in the distance can no longer be seen, visitation in the parks may drop off and lead to a decline in revenue. Beyond just a drop in visitation, while visibility is poor, this can even negatively impact their visitation rates in the future since disappointed visitors
will be less likely to come back and recommend it to others.
Three of the most affected parks in the U.S. include Grand Canyon National Park, Sequoia National Park, and Great Smoky Mountains National Park. All three of these parks are renowned for their scenic vistas and are thus highly susceptible to the effects of poor visibility. Furthermore, these parks are located in areas where the effects of human activity and the weather can combine to frequently produce hazy conditions. Pictures of the Great Smoky Mountains are shown comparing a clear view to an obscured one. Before the Clean Air Act was passed in 1970, haze in many areas of the country was extremely high. The amount of haze has dropped off somewhat after its passage. However, haze has likely increased in recent years as, among other things, population has increased and wildfires have become larger and more common. To investigate the effects of air quality on visibility, data must first be gathered in order to draw conclusions. Much of this process will involve the comparison of historical air quality data to that gathered in the current day. The historical air quality data will be used to establish a baseline and determine whether the concentration of the contaminants of interest have changed over time, which can then be used to show how the visibility in these areas has shifted over time. There are an abundance of organizations and agencies from which extensive historical air quality data can be found, including but not limited to the Environmental Protection Agency, National Oceanic and Atmospheric Administration, U.S. Forest Service, National Park Service, and the Interagency Monitoring of Protected Visual Environments. In particular, IMPROVE has been continuously monitoring air quality and its effects on visibility across the country since 1985 and has expanded to the point where it now has 110 primary monitoring sites with about 50 additional sites which can be used for expanded coverage. By using identical equipment at each site, the data is directly comparable to that from other sites. Many of these sites are located within national parks, including all three of the primary parks of interest to this project. Through strategic placement, these sites can effectively monitor the air quality in the airsheds of 155 out of the 156 federally protected Class 1 areas around the country.
The 5 species which have the largest contribution to haze are sulfates, nitrates, organic carbon, elemental carbon, and crustal material. The amount of impact each has on visibility varies throughout the country and the seasons, depending on how much of each is present at the time, but the approximate impact each has on the eastern and western portions of the United States can be seen in this figure. Sulfates are the most abundant constituent of haze that impacts visibility throughout the United States. Through a series of chemical reactions, sulfate particles can form from sulfur dioxide gas, which is primarily released from industrial and commercial equipment such as coal-fired power plants, smelters, and industrial boilers. Sulfates make up a larger portion of haze in the eastern United States due to the higher number of coal-fired power plants in the region. High humidity can accelerate the growth of sulfate particles to the point that they become very efficient at scattering light and thus impact visibility even more. Nitrates exhibit a similar property in human conditions, but nitrates are primarily emitted during the type of high-temperature combustion that takes place in most engines. Other forms of nitrogen, such as nitrogen oxides, are also emitted as a result of combustion. These combustion sources include power plants, cars and trucks, boats, construction and yardwork equipment, and a variety of industrial combustion sources. Organic carbon can be either emitted directly from a point source or be produced through the reaction of gaseous hydrocarbons in the air. Point sources can include combustion activities, but a large part of emissions are derived from the evaporation of a wide variety of volatile compounds, including gasoline, paints, and industrial solvents. While organic carbons are usually emitted through the natural volatilization of VOCs, Elemental carbon is mostly emitted as soot. All previously mentioned constituents of haze largely scatter light, but elemental carbon primarily absorbs light. It can be emitted in nearly any combustion process, but is more prevalent in processes where the combustion is relatively inefficient, such as forest fires. Due to the extremely large scale that forest fires can reach, along with the extreme heat differential they create that can transport soot high into the atmosphere, forest fires are quickly becoming a larger component of haze in the western United States, especially in the summer and fall months. The final major contaminant of interest that severely impacts visibility is crustal material, which is essentially dust. Crustal material is most prominent in areas that lack foliage ground cover, making it especially impactful in areas such as deserts, which can have large amounts of loose soil that is exposed to constant wind. Crustal material also enters the atmosphere through construction activities, the passage of vehicles over dirt roads, and by general wind erosion in nearly any area.
3 different instruments were looked at to aid in measuring visibility in air. The first one is the nephelometer, which measures the light scattering of a sample. This sample can be either an open environmental sample that is drawn into the chamber on site, or is bottled beforehand and transferred to the nephelometer for testing. A halogen lamp within the measurement chamber illuminates the sensing volume with a known intensity over a range of 7 degrees to 170 degrees to the perpendicular. This light is then scattered by the aerosol. In this image, the sensors are on the left end of the tube and are looking down the barrel to the right. To minimize the effects of reflected light off the far end influencing the measurements, a light trap at the opposite end absorbs a high percentage of the light which strikes the surface.
Through careful calibration
And the input of proper data during setup, the instruments can also account for light scattered by gases present in the chamber, light reflected off the walls of the instrument itself, and any additional background noise which might adversely affect the readings. On the left end of the tube, the light passes through a rotating disc which contains 3 different lenses. The first allows light to pass through unaltered and constitutes the portion of the light which will be used for measuring the scattering. The second lens is completely opaque and allows no light to pass through, which is essential for calibrating the instrument to correct for the background noise. The third lens allows only a small fraction of light to pass through, which aids in measuring the stability in the output of the halogen lamp. The rotating disc apparatus,
commonly
referred to as the chopper, makes about 23 full rotations per second, thereby ensuring that the instrument is continuously calibrated. After the light passes through the chopper, it is then focused by a lens and either passes through or is reflected by a set of dichroic filters. This ensures that only a specific range of wavelengths are transmitted to each of 3 different photomultiplier tubes, which convert the influx of photons into an electrical signal which can be interpreted as intensity. Each of the 3 photomultiplier tubes is uniquely sensitive to the small range of wavelengths which the dichroic filters selected for, and roughly correspond to the red, green, and blue visible wavelengths. With the intensity of the light scattered by the aerosol itself measured in relation to the known intensity of the lamp, the extinction coefficient can be calculated. This is essentially a measurement of how much light is expected to be scattered away and absorbed over a given distance. By plugging this
extinction coefficient
into Koch-Mider's formula, the visibility can be calculated for the given conditions. The nephelometer can also account for changes in humidity and temperature, and can be configured to measure only backscattering or total scattering. In total scattering, the halogen lamp illuminates the chamber over an angle of 70 to 170 degrees as before. For backscattering, part of the range is reduced by covering the leftmost portion of the lamp and only allowing light to enter at 90 to 170 degrees to the chamber. The downside to using nephelometers for this particular study is that they do not provide any information about the concentration of the constituent contaminants, only about their combined effects upon visibility. The spectrophotometer is another instrument which can be used to measure visibility. The basic principle which it relies on is that every chemical substance absorbs light within a certain range of wavelengths. The spectrophotometer works by focusing a light source of known intensity through a lens and then splitting it into its constituent wavelengths with a prism. A slit screen selects for a particular wavelength that is defined by the user, and this light of known energy and intensity then transmits over a defined path length that contains the sample. The light then impacts a sensor on the opposite side of the chamber and is converted into an electrical signal which can be analyzed mathematically. The spectrophotometer can be used to determine not only the extinction coefficient of a particular sample, but also the concentration of the constituents present within the sample. Because the path length and light scattering and absorbing properties of the target and contaminant are known, Its concentration can be determined as a function of the drop in the intensity of the light source which reaches the photosensor. With the concentration of the substance within the sample now known, its expected contribution to visibility loss over a given distance can be calculated in much the same ways as it was for the nephelometer. By summing the drop in visibility over all of the wavelengths for which a substance absorbs light, the spectrophotometer can be used to find the total drop in visibility on a given day that is attributable to the largest 5 contributors in haze, which were discussed previously. As a result, the expected visibility can be obtained, and you can determine whether or not haze is the driving factor in visibility changes. The air filtration method is a more indirect way to determine the visibility on a given day, and is the method which the Improved Network, the Interagency Monitoring of Protected Visual Environments, uses. For their setup, 4 independent samplers collect particulate matter at the PM2.5 and PM10 scale. The first module uses a Teflon filter that is analyzed for gravimetric fine mass and elemental carbon concentration. The second filter is made of nylon and analyzes for sulfate anions, nitrates, nitrite, and chloride using ion chromatography. The third module utilizes a quartz fiber filter that uses thermal optical reflectance to detect organic and elemental carbon. The fourth module is equipped with an inlet that only allows particles of PM10 or smaller to pass through, where a Teflon filter then catches any aerosols and is gravimetrically analyzed to determine the total loss. Air filtration is a useful method for data analysis because it provides data which can be analyzed by multiple means. It stores what amounts to a physical record of the data which can be reanalyzed later if need be, and it can be used as a standalone method. Through knowledge of how these different contaminants interact with light, and knowing the total airflow over the filters in each of the individual modules, it is possible to determine the concentration of each contaminant and then use that information to calculate the visibility reduction that day due to haze.
Data collection methods like the ones discussed earlier can help determine the steps policymakers take to address visibility and pollution problems. For example, it was mentioned that the U.S. passed a federal law in 1970 called the Clean Air Act. Not only was this law passed as a response to the visible smog above industrial areas and cities, but it also had the purpose of reducing the emission of
pollutants
that endangered public health and welfare. The Clean Air Act requires the EPA to set the national ambient air quality standards for specific widespread pollutants based on scientific testing. One effect of the Clean Air Act is that between 1980 and 2010, it has helped reduce emissions of the main acid rain-causing pollutants, sulfur dioxide and nitrogen dioxide, by 71% and 46% respectively. This type of process has been used many times in the past to determine problematic pollutants and their sources, and can similarly be used for our national parks. Grand Canyon National Park, along with many others, occasionally experience visibility issues as a result of low-quality air. This can happen due to temperature inversions where warm air higher in the atmosphere traps cooler air beneath it, which keeps smoke and haze inside of the valleys. In these areas, the air can be tested by using the nephelometer and/or the spectrophotometer to first determine how much light is being absorbed and reflected. Next, the constituent concentrations in the air
can be determined
by using air filtration methods to collect the pollutants, allowing for targeted analysis of specific air pollutants. Finally, after determining the contributors of the haze, national parks can use the data to implement new policies and help alleviate the visibility problem. The group has discussed how pollutants are not only capable of causing harm to human health, but also how they contribute to the creation of haze. Haze can negatively impact experiences at our national parks by reducing the visibility of the air, ruining what should be good views. It has been mentioned that the 5 main constituents that contribute to haze are sulfates, nitrates, organic carbons, elemental carbon, and crustal material. By using tools and methods like nephelometers, spectrophotometers, and air filtration, we can determine how big of a problem haze is becoming, as well as what specifically is causing it in each area. The utilization of these tools is key to understanding how the haze in different national parks should be handled. Once the data is collected by researchers, it is up to them to educate policymakers so they can take appropriate measures to help reduce the formation of harmful haze. It is important to note that human activity is responsible for most of the constituents that cause haze, and limitations on certain human actions is the most likely solution for this problem.
I should have pretended to cut that. Like, oh yeah, that's not there anymore, and then put it in as a blooper. You know what? We're learning.
This can happen due to temperature inversions where warm air higher.
Fudge. Very good. We'll just cut it in. You'll never know.
Right.
Look, I stopped recording.
Yeah.